All right, good morning, grade 11s. This is probably what I'm going to show you here today is probably the hardest. Well, okay, let me say it like this. It's not that hard, but it's probably in the last unit, in the electricity unit, the most difficult type of problem. Okay, so on a test, you need to be able to do questions like this. And so there's a couple of questions in the homework that are quite challenging. Okay, so and I don't want to put you off. Some of you will not find it that challenging, but some of you will, and so I just wanted to give you a little heads up there. Anyway, it starts off pretty straightforward. We're going to be talking about series and parallel circuits, and so I wanted to show you this just with this demonstration here at first. Now we know we've looked at this already. What happens when you connect more than one device in a circuit? Well, it's pretty straightforward. There's two ways of doing that. Okay, and for us, I'm going to use these 3 lights. Actually, why don't I use 2 lights and 1 resistor? Okay, they don't have to be the same kind of device. I'm just going to lay these out here like this. Now nothing's turned on because there is no power supply connected, so I need some wire to connect everything together. So I'll do that. Nothing happening yet because the circuit is not complete. So one way to connect it all together is kind of like everybody's holding hands. And this is called a series circuit. So they're all connected here like this. So that is a series circuit. Okay. And what happens is in a series circuit, and you can see here, okay, what it looks like in a series circuit. Everything is connected one after the other along the path, and that's what series means. It means one after the other. Okay, so that's a series circuit. Now there's a couple of things you'll notice. Number one, the current is the same everywhere in the series circuit. Okay, does that make sense to you? There's only one path, and according to Kirchhoff's laws, the current must be the same everywhere along that path. So if it's 1 amp coming out of the power supply, it has to be 1 amp everywhere. Okay, so in other words, like everyone's moving at the same rate. If you look at the electrons, everyone's moving at the same rate, because they are sort of like the chain in a bicycle must move at the same rate. Like they're all moving together along that one single path, and there's really no way for anyone to move faster or slower in any one spot. You can speed them all up by pushing harder on, the pedals here. Okay, that'll make it go a little faster, but still everyone moves at the same rate. Okay, so I can get more current by pushing more with more force with my battery, if you like, but I still get the same current in all 3 devices. Okay, so the current is the same everywhere. Now the voltages do not have to be the same. Okay, and what I'll do is I'm just going to click on these things and I'll change their resistance. Okay, and I'll actually make them like so that they're all different. Here, I'll make this one lower. And what's this one, 10? Okay, so I'll make this one whatever. Let's make it 9. Here, let's make it 6. And what did I make the resistor? 6.5. Okay, let me change that to 15. All right. Okay, so here's the deal. They each get the same current, but they don't necessarily have the same voltage. So to show you that, let me show you this voltmeter here. The battery voltage that I set it to was 37.5. Now let me change that number a little bit. Let's change it to 50. Okay, so I have 50 volts. Now what happens is if I were to measure the voltage drop across the first light bulb, I get 31.93. Okay, and then the second one, the resistor, I get 13.03. And the third one, okay, my last device, oh, I've got it backwards, hang on. I got 5.04. Now, if you add up those numbers, you'll notice they add to 50, okay, which is the voltage across my source, okay, 50 volts. So what happens is the 3 individual loads, the 3 devices, will together use up all the voltage, but they don't have to do it equally, okay? But they all have to have the same current, So the current is the same everywhere, and I'm not gonna show you the measurement of current here. You can see that it's the same everywhere. Okay, and that's it. So that's how you connect devices in a series circuit. And what we notice in a series circuit is the voltages have to add up. The voltage drop along a single path has to add up to the voltage in the power supply. That makes sense, okay? But the voltages are not the same, but they do add together. But the current has to be the same everywhere, and that's a property of a series circuit. All right, so now let's remove this. Let's break our connections, okay? And let's connect these things a different way. Okay, so I'm going to break all these connections here so that I have my devices, and I'm going to line them up differently. Okay, I'm going to line them up like this. And now what I'm going to do is I'm going to attach each one. Actually, let me break that. I'm going to use more wire, since I'm not limited by wire here, just to illustrate it a little differently. Okay, I'm going to do this. I'm going to take this wire, stick it here, and that wire there. Okay, so there's one light connected by itself so far. Okay, I'm going to zoom out a little. I'm going to move this light up. Whoops, I need to rotate it. I'm just going to move it up here. And I'm going to move the resistor up here. All right, now I'm going to create a junction here and then add another wire here. So what I'm doing is constructing another circuit, but this one, and I know I'm using, I could use less wire, okay, but I want to make it as clear as I can. So, all right, now I just have to connect my third light, and I'll do it like this. One more wire will do it. I'll make another junction here. All right, so here's the deal. This okay, I'm trying to scroll around on this. Okay. I mean, if you ever want to play with this, you can see the website at the top. All right, let's just look at it like this. All right, so here we see the three things, okay, all connected together in the circuit, and they're connected in a very different way this time. This is called a parallel circuit, so there's parallel paths, okay? And what's happening is each branch of the parallel circuit has a different amount of current flowing in it, okay? So here's the thing. I'm going to try this. Okay, good. All right, so this is sort of, we call this a clamp meter. Okay, it's able to measure the current in a wire without actually being thrown into the circuit like a way you would normally connect an ammeter. Okay, so here's the deal. If I measure the current here, the current coming out of the battery is 12.87 amps. Now it's still 50 volts here on my power supply. I haven't changed anything, okay? But now if I take my voltmeter and I measure across the first light, what I notice is it's 50, okay? Now if I take it across the second resistor, second load, it's also 50. If I do it across the third load, it's also 50. In fact, it's 50 everywhere, including the battery. So the voltages are all the same. But that kind of makes sense, because what happens is, you know, if you take one path, so what's happening is an electron that takes the first path has to drop all of its energy before it goes back to the battery. Well, it's only going through one light. It's only going through that first light, so this light right here. So if you take that path and you go back to the battery, you're going to lose all your voltage, okay, just through that one light. So you're going to lose all 50. Now if you take the second path, you have to lose all 50 through the second device. Okay, and if you take the third path, you'll lose 50 volts going through that third light bulb. So all the voltages are the same, but the current is not the same. So look, the current coming out of the battery is 12.87 amps. Well, the current going through the first light is only 1.32. Okay? The current going through the second resistor is 3.23. Okay? And then finally, the current going through the last light is 8.33. Now, if you add those three numbers up together, you'll find that they add up to give you 12.87 amps. So here the current adds up to give you the total amount of current, but the voltage, okay, is equal everywhere. Okay, so it's kind of like the opposite of the series circuit, right? So this is called a parallel circuit. Parallel because it has a number of parallel pathways, okay? And what happens is these parallel paths each have a different amount of resistance, so they draw a different amount of current, okay? But the currents will add together to give you the total current, and unlike a series circuit where the current's just the same number everywhere, okay? There's only one single path there. All right, so anyway, I just wanted to show you this as a demonstration. Now we're going to look at the notes in a separate video, and I'm going to stop this here.